Welcome to another deep dive. Today, we're taking a look at the Lambda calculus. And I think, especially for you, coming from a philosophical background, this is going to be pretty interesting. We're going to be looking at this concept that's really fundamental to mathematics, to computer science, to logic, and even to philosophy itself.
Absolutely. And the source material that we're going to be using for this deep dive is the Stanford Encyclopedia of Philosophy's entry on the Lambda calculus. And our mission here is to take this really comprehensive resource and to pull out some of the most significant philosophical ideas. And in particular, we're going to be focusing on how Lambda calculus helps us think about functions and relations.
You know, as a philosopher, you've probably thought a lot about questions like the foundations of mathematics or the philosophy of language. And we're going to be looking at a system today that has had a really big impact on both of those areas. So what is this Lambda calculus all about? Like, at its core, what is the idea here?
Okay, so the Lambda calculus is a way of writing down functions. It's a way of describing how they operate on inputs. And it's really simple. It's got really simple building blocks. So there are variables like x, y, z, and there's a way of saying apply one thing to another. So that's written as just two things next to each other, mn. And then there's a really crucial operation called abstraction, and that's written with a lambda xm. And it's the last part, the abstraction. This is how we define functions. And it says, okay, you can think of this as taking an input x, and the output of this function is going to be whatever this expression m is.
So let's make that a little bit more concrete. Let's think about a polynomial that you might encounter in math. So something like by 2x plus 5. How would we represent that in the Lambda calculus?
We can use the Lambda calculus to abstract over this to create a function that computes this polynomial for any given input. And so what we would write is lambda by 2x plus 5. And if we want to see what this function does to a specific number like 2, we would write lambda by 2x plus 5, 2.
And this is where we get to this concept of beta reduction, right?
Exactly. So lambda by 2x plus 5, 2 through beta reduction becomes 22, 2x plus 5. And so basically what's happening is that the 2 is being plugged into the x within that function. And the more general rule for that is lambda xmn becomes mxn. And so you can think of beta reduction as sort of the heart of Lambda calculus. It's like the engine, the mechanism that makes it all work.
So the beta reduction is the doing, the calculation. Now, what about functions that take more than one input? So for example, if I'm thinking about like the length of a hypotenuse of a right triangle, right? I need two inputs for that. I need the length of both of the sides. And the formula, of course, is going to be like square root of a2 plus b. So how does the Lambda calculus handle functions that have more than one input?
Yeah, so it uses a technique called currying. And basically what it does is it takes a function of multiple arguments and turns it into a sequence of functions of one argument. So for example, if we wanted to think about calculating the hypotenuse, we could write that as lambda b star t d plus b2. And so here what we're doing is we're taking a as an input, and then that gives you a function that takes b as an input.
Okay, so let's say I want to calculate the hypotenuse of a triangle with sides 3 and 4, right? So I take my function, which is lambda ab square d plus b2, and I apply that to 3. What happens?
So through beta reduction, you get lambda b squared t plus b2, which is a function that you can then apply 4 to.
Right. So then I would take that and apply it to 4, and that's going to give me through beta reduction plus 42, which of course is 5. So it's like the function consumes its arguments one at a time. It produces this intermediate function, and then it consumes the next argument until it's got everything it needs to give you the final answer.
Right. And so this is actually kind of an interesting philosophical point because it gives us a different perspective on what functions are. So the standard view from set theory, a function is thought of as basically a set of pairs, right? So input-output pairs. But Lambda calculus gives us this other perspective where we think about a function as this sort of rule, this procedure for taking inputs and transforming them. And this brings us to this distinction between the extensional and the non-extensional view of functions.
So this is where it starts to get really interesting for us philosophers. So in set theory, functions are extensional, meaning that two functions are the same if and only if they produce the same output for every possible input. It's all about the what, not the how.
Right. But Lambda calculus allows us to distinguish between functions even if they always give you the same output. So if you have two lambda terms, let's say lambda xm and lambda xn, if for every possible input that you could give them, they give you the same output after you've reduced them as much as possible, then those two terms are said to be extensionally equivalent.
So for example, we can think about lambda xx plus 1 and lambda x plus 2. From a purely mathematical standpoint, these are the same function, right? Any number you plug in for rock is going to give you the same result. And they're even what philosophers might call intentionally equivalent. That is, in any possible world where basic arithmetic holds, these two expressions are going to pick out the same mapping from input to output.
Right, but in Lambda calculus, they're not automatically treated as identical. So they represent different sequences of operations, different rules for getting from the input to the output. And that's why Lambda calculus is often described as being non-extensional. Some even argue that it's hyper-intentional.
Hyper-intentional. So that means that two things can have the same intention, so the same meaning or the same conceptual content, but they're still distinct. So in the Lambda calculus, even if two functions are intentionally equivalent, so they give you the same output in all possible worlds, they might still be different if the actual sort of sequence of lambdas and applications, if the actual calculation that they represent is different. It's kind of like the algorithm or the recipe matters, not just the final dish that gets produced.
That's a really great way of putting it. And so this hyperintentionality is one of the reasons why the Lambda calculus is so valuable as a tool in philosophy of language for thinking about the meanings of expressions, and also in metaphysics when we're thinking about things like the nature of properties and relations, which we'll get to later. But before we get too far into the philosophical stuff, I think it's important to sort of nail down some of the basic syntax of the Lambda calculus in a little bit more detail.
Okay, so far we've covered the three fundamental ways that you can build these Lambda terms. You have the variables, you have the application, and you have the abstraction. What else do we need to know?
Okay, so we need to know the formal rules for forming Lambda terms. So we have the variables, the application, and the abstraction. Those are the three things that you can use. And then, just to cut down on parentheses, we have a convention that applications associate to the left. So if you see M1, M2, M3, that should be read as M1, M2, M3.
Okay, so applications group from left to right. Now, we talked a little bit about bound variables. These are the variables that are like captured by a lambda. What about the other variables?
Right, so those are called free variables. So we have a way of defining these. So for variable x, the free variables of x are just x, and there are no bound variables. For an application mn, the free variables of that are just all of the free variables of m together with all the free variables of m. Same for the bound variables, and then for the abstraction for lambda xm, the free variables of that are all of the free variables of m except for x, because x is now bound by the lambda. And the bound variables are all the bound variables of m plus x. And if you have a lambda term and it has no free variables at all, then that's called a combinator. You can think of a combinator as a fully specified operation. It's all there.
Combinators sound pretty important, and especially when we start thinking about building more complex systems from these basic elements. Maybe we can come back to combinators in a bit. Before we do that, we need to understand this concept of substitution. So when we perform beta reduction, we're replacing an x with an n in an m. And so the notation for that is mx. And what exactly are the rules for this substitution?
So the substitution, mxn, means you replace all of the free occurrences of the variable x in m with n. And we can go through the formal rules for that. So if m is just the variable x, then xn is just n. If n is a variable y and y is different from x, then yxn is just y because we're only substituting for x. If m is an application, n is just you substitute in both the a and the b. So you get x n b x n. If m is an abstraction, so lambda x n is just lambda x n, because the x is not free in that expression. And then finally, if m to y is different from x, then lambda yxn is lambda yxn. So you continue the substitution within the body of the lambda.
Okay, so that sort of lays out the step-by-step process. But there's this thing that can go wrong. There's this thing where if we're not careful about the variable names that we're using, something can go haywire during the substitution process. Can you explain that?
Yeah, so this is where alpha convertibility comes in.
Yeah.
So basically, we have to be careful when we're substituting a term n for n, that no free variables in n accidentally become bound in the process. That's called variable capture. And we don't want that to happen because that can change the meaning of the expression.
Can you give an example of how that might happen and how this alpha conversion helps?
Yeah, so for example, let's say we have the term lambda x lambda yx y5, and we want to apply that to 2y. Now, if we were to just substitute 2y, we would get lambda y2y. And you see what's happened there. The y that was free in 2y is now being captured by this lambda.
Right, so that's not good.
Yeah, and so what we want to do is we want to alpha convert the lambda ixy. So before we do the substitution, we can rename that to something else like z. So we get lambda zx5. And now if we apply that to 2y, then we'll get lambda zai. And here the y is still free, which is what we want. And so two lambda terms are alpha convertible if one can be obtained from the other just by renaming bound variables.
Okay, so that makes this whole process of beta reduction a lot more clear. Now let's go back to those combinators that we were talking about earlier. So you said that they were completely specified operations. They didn't have any free variables. So can you give some examples of these combinators and maybe talk about like what they mean, what they do, and maybe what their philosophical significance is?
Yeah, absolutely. So some of the most basic combinators are very elegant. So for example, we have the identity combinator, mathBFI, which is defined as lambda x dex. And it's very simple. It just takes an input and it gives you back that input. Then we have the mathBFK combinator, sometimes called the kestrel, which is defined as lambda x lambda yx. So if you give the mathBFK combinator an input m, it's going to give you back a function that always returns m no matter what input you give it. And in a logical setting, this can be thought of as the truth value true, which is sometimes denoted as mathBFT.
So the mathBFK combinator basically lets you discard an argument and always return a constant value. What about something that actually uses both of its inputs?
Right, so there's the mathBFS combinator, which is sometimes called the Starling, and that one is defined as lambda x lambda u lambda z x z. And that one is a little bit more complicated, but the basic idea is that it takes two functions, x and y, and then an argument applies y, and then applies the result of the first application to the result of the second. Our source also mentions the mathBFB combinator, which is for function composition, lambda lambda u lambda y. And then the truth value false, which is sometimes written as mathBFS, is often defined as lambda x lambda y, which is equivalent to mathBFKI.
Okay, so it takes an input, and then when you give it a second input, it just returns the second input.
Right. And then we have some more interesting combinators. So we have the bold symbol omega combinator, which is defined as lambda x, and then we have bold symbol omega, which is bold symbol applied to itself. So bold symbol omega. And this leads to an infinite loop of reductions. And so bold symbol omega are interesting because they show that the lambda calculus can express self-application, and they can also express these computations that never terminate. And then we also have the fixed point combinators, which are y and zeta. And these are kind of mind-bending. But what they do is that they take a function and they return a fixed point of that function.
Okay, so for example, if you applied the y combinator to a function f, you would get something that reduces to f applied to y.
Right. And so these fixed point combinators allow us to define recursive functions within the lambda calculus without explicitly using recursion.
Wow, so recursion without recursion, that's pretty wild. Now, so far we've talked mostly about beta reduction as like the main way that lambda terms simplify, but you mentioned this thing called eta reduction earlier. Can you tell us about that?
Yeah. So eta reduction is another rule for simplifying expressions. And it says that if you have a term of the form lambda x mx, where x natives that occur free in m, then that can be simplified to just m. So the idea is that if you have a function that takes an argument and then applies m to it, and m doesn't even depend on x, then that's essentially the same as just having m. And then in addition to beta reduction and eta reduction, we have beta reduction, which is just a combination of the two.
And just like with beta reduction, you can have these sequences of reductions, or you can have a mixture of the two. Now, when you have a term that has multiple places where you could apply these reduction rules, does the order in which you apply the rules matter?
Yes, it does matter. So a beta redex is any term of the form lambda xpq. So that's a term where you could apply a beta reduction. And a term is in beta normal form if there are no beta redexes in it. So you can't reduce it any further using beta reduction. And the problem is that if a term has multiple redexes, the order in which you choose to reduce them can affect whether you reach a normal form and also how quickly you get there.
Our source material mentions these different strategies for choosing which redex to reduce, like always picking the rightmost one or always picking the leftmost one. And it says that some of these strategies, they might not actually find a normal form, even if a normal form exists.
That's right. So if you consider the term, for example, mathBFK ionica, where mathBFK is lambda, mathBFI is lambda g. If you use a leftmost reduction strategy, then what you would do is you would first look at mathBFKI, which reduces to lambda ti, and then if you apply that to bold symbol omega, which hasn't been reduced yet, you get mathBFI, which is in normal form. But if you would choose to reduce the rightmost redex first, then bold symbol reduces to itself, so it just keeps going on forever.
And you would never get to the math BFKI part.
Right. But the leftmost reduction strategy has this nice property that it's normalizing. So if a term has a beta normal form, then the leftmost reduction strategy is guaranteed to find it.
Okay, so that's good to know. So we've been talking about reduction, which is about simplifying expressions. But we can also think about when two lambda terms should be considered equal. And this brings us to this idea of lambda theories, which are theories that try to formally define the properties of equality in the lambda calculus.
Right, so instead of just saying that two terms reduce to the same normal form, we can actually take equality as a primitive notion, and we can give axioms that tell us how equality works. So we have the basic rules of equality, so things like reflexivity, everything is equal to itself, symmetry, if x is equal to y, then y is equal to x, and transitivity. If x is equal to y and y is equal to z, then x is equal to z. And then we also have rules that are specific to application and abstraction. So for example, if m is equal to n, then applying something to m is the same as applying it to n. And similarly, if m is equal to n, then abstracting over m is the same as abstracting over n.
And the most important rule, the one that really captures the essence of the lambda calculus, is this beta rule itself. And now we can express that rule as an equality. So we can say lambda xmn is equal to mxn, and that's really the heart of the basic lambda theory, which is usually written as just lambda.
Right. And then we can get stronger theories by adding additional axioms. So for example, we could add the eta rule as an equality, so lambda x mx if mn x ns. And this would give us a theory that incorporates extensionality. And there are even stronger extensionality principles that you could add, like the rule math bx, which says that if for all x, mx, then mn. And there's also the omega rule, which is another very strong form of extensionality.
So by adding these different principles, we can sort of create this whole spectrum of lambda theories, some of them where the notion of equality is stricter than others, and that reflects, I guess, different philosophical stances on like when two functions should be considered fundamentally the same. Now, one thing that we want for any formal system is for it to be consistent. So what does it mean for the lambda calculus to be consistent, especially since it's not really a system for proving logical statements in like the traditional sense?
Well, in the case of the lambda calculus, consistency means that not every equation is provable. So if a theory were inconsistent, it would mean that you could prove that, anything was equal to anything else. For example, that the combinator, which is a constant function, was equal to the combinator of math BFO, which is the identity function. And that just shouldn't be true, intuitively.
And the Church-Rosser theorem, which you mentioned earlier in the context of reduction, this also plays a really important role in this idea of consistency for the lambda calculus, right?
Right. So the Church-Rosser theorem says that if a term can be reduced in two different ways, then you can always find a common term that both of those reduced terms can be reduced to. And this has a really important consequence for equality. It tells us that if two terms have distinct normal forms, then they cannot be proven equal in the theory, lambda. And so because the normal forms of math BFK are distinct, their equality can't be proven, and that means that the theory is consistent.
That makes sense. Okay, so we've talked a lot about the syntax of the lambda calculus. We've talked about the rules for manipulating lambda terms. But what about the meaning? Like, how do we actually give a semantics to this system? And our source material suggests that this has been a surprisingly difficult problem.
Yeah, it has been difficult. So the most natural idea is to just interpret lambda terms as functions. But if you think about functions as sets of ordered pairs, then that runs into problems when you start thinking about self-application. Because that would mean that a function was applying to itself. And so a set would have to contain itself as a member.
Which is a no-no.
Right, right. And even if we switch from thinking about functions as sets of ordered pairs to thinking about them as rules or procedures, we still run into trouble when we try to define the domain of these functions. Because in the untyped lambda calculus, everything can be both a function and an argument. And so we need a domain that can contain everything.
So it seems like finding a kind of standard set theoretic model for the lambda calculus is really, really tricky.
It is tricky, but it can be done. So Dana Scott in 1969 actually came up with the first model, which is called Dean-Fay, and that uses some pretty sophisticated math to construct it. But for our purposes, I think it's better to just think about what a model of the lambda calculus should be more generally. And so our source talks about these things called syntactical lambda models.
Okay, so what are these syntactical lambda models, and how do they help us understand what lambda terms mean?
Right, so a syntactical lambda model is based on what's called an applicative structure. And that's just a pair where D is a set, a non-empty set, and C dot is an operation on D. So it takes two elements of D and gives you back an element of D, and then on top of that you add an interpretation function, which takes a lambda term and gives it a meaning in D. And it's designed to mirror the reduction rules of the lambda calculus. So in particular, it has to satisfy the beta rule and also what's called the rule, which says if lambda xm, lambda xn.
So in these syntactical models, the meaning of a lambda term is basically determined by how it behaves syntactically.
Yeah, pretty much.
Yeah.
And while these models are sound, so anything that's provable in the theory, lambda is going to be two of these models, they can sometimes feel a bit circular or not very illuminating. It's like you're defining the meaning of something just by saying how it behaves rather than actually explaining what it means.
Right. So it seems very tied to the syntax. How do we even know that these models exist? Like, can we actually construct them?
We can. So the simplest way to construct a model is to use what's called the term model. And in the term model, the elements of D are just the lambda terms themselves. And the application operation is just syntactic application. So to apply one term to another, you just write them next to each other. And then the interpretation function just maps each term to itself.
Okay, so that's reassuring. So we have ways of building these models. But our source material also mentions these things called syntax-free lambda models, which it says are maybe a little more satisfying. So what's the difference between these syntax-free models and the syntactic ones that we were just talking about?
Right. So in a syntax-free model, the meaning of a lambda term is not tied to its syntactic structure. So instead of just mimicking the reduction rules, syntax-free models define abstract properties that the applicative structure has to satisfy. And the meaning of a lambda term is then determined by its relationship to those properties. So it's more compositional. The meaning of a complex term is built up from the meanings of its parts. And interestingly, it turns out that these two kinds of models, the syntactic ones and the syntax-free ones, are actually equivalent in a certain sense.
So despite the initial challenges, we do have these robust ways of giving meaning to the expressions of the lambda calculus. Now, our source material also talks about some extensions of the lambda calculus and some related systems. So in particular, it talks about this thing called combinatory logic. You mentioned this briefly earlier. How exactly does combinatory logic relate to the lambda calculus?
Okay, so combinatory logic is a system that was developed around the same time as the lambda calculus. And it has a really interesting feature, which is that it doesn't have any variables. So instead of using lambda abstraction, it uses these things called combinators, which are these basic functions that can be combined to form other functions. And despite the fact that there are no variables in combinatory logic, it turns out that it's just as expressive as the lambda calculus. So you can translate any lambda term into an equivalent term in combinatory logic.
So it can do all the same stuff without variables.
Yeah. And some simple examples of this translation. The lambda term, lambda YY, translates to the mathbfi combinator, which remember just returns whatever you give it. And then lambda x lambda YX's translates to a term in combinatory logic that's built out of mathbfk. So that's a pretty profound connection. It's kind of amazing that you can do all of this without variables. It really shows how fundamental function application is. And what about adding types to the lambda calculus? Our source mentions this idea of adding types. What does that do? Right. So adding types to the lambda calculus is basically a way of being more careful about what kinds of things you're allowed to apply functions to. So, for example, you might have a type for numbers and a type for functions from numbers to numbers. And then the typing rules would say that you're not allowed to apply a number to a number, or you're not allowed to apply a function to something that's not a number. And this leads to the field of type theory.
So we go from the untyped lambda calculus to the typed lambda calculus.
Exactly.
And that gives us a way to rule out certain kinds of nonsensical expressions that might be possible in the untyped version. Now, the last major section in our source material is about applications. And it looks like lambda calculus has quite a bit of philosophical relevance, especially when it comes to logic and relations.
Right. So maybe we could start by thinking about logic. Our source material calls it logic a lambda. And we already saw how the combinators and represent truth values, and we can even define things like an if-then-else connective in terms of lambda terms. But it turns out that the connection between lambda calculus and logic is much deeper than that. And this is where we get to the Curry-Howard correspondence.
Ah, yes, the Curry-Howard correspondence, or I guess some people call it the Curry-Howard-de Bruijn correspondence. So what is that about?
Right, so this is this amazing correspondence between propositions in logic and types in typed lambda calculus. So if we think of a function type, sigma right over tau, as representing implication and logic, so sigma right over tau. And if we think of type variables as being propositional variables, then it turns out that the types of some of the basic combinators correspond to tautologies in logic. So, for example, the identity combinator has the type A right O A, and that corresponds to the tautology A right O A. Similarly, the math BFK combinator has the type A right arrow A, which corresponds to the tautology A right arrow A.
Right. And so the really cool thing about the Curry-Howard correspondence is that it tells us that if you have a lambda term that has a certain type in a typed lambda calculus, then the proposition that corresponds to that type is provable in a certain system of logic, which is called intuitionistic logic. And conversely, any proposition that's provable in intuitionistic logic can be expressed as the type of some lambda term. So this means that you can actually think of lambda terms as being proofs.
Right. And this has had a huge impact on logic and also on computer science, especially in the area of programming languages.
So it's this really deep connection between computation, as represented by the lambda calculus, and logical reasoning, as represented by this intuitionistic logic. So we're seeing how the lambda calculus can be used to model logic. What about relations?
Right. So for relations, the idea is to think of a lambda term of the form, lambda xm, not as a function, but as a property or as a relation. So we can think of lambda xm as representing the property of being an x such that m is true. And then applying a term m to a term n can be thought of as saying that n has the property m.
So, for example, if you have the lambda term lambda x and you apply it to the term you, which represents you, the listener, then that would mean you are a philosopher.
Right. And this is connected to this area of metaphysics called property theory, where properties and relations are treated as being these fundamental constituents of reality. And lambda calculus is used to build up these complex properties and relations. So, for example, you could have the property of being loved by John, which would be lambda hex loves.
And these property theories, they often have to be careful about how they use beta reduction, because if you allow unrestricted beta reduction, you can end up with paradoxes, like Russell's paradox. But the fact that lambda calculus is hyperintentional makes it very useful in these property theories, because it allows you to make distinctions between properties that might be extensionally equivalent, but that we think of as being conceptually distinct.
Exactly. And the source material even makes this argument that the relational interpretation of lambda terms might be more fundamental than the functional interpretation, even in mathematics. And this just shows how versatile the lambda calculus is.
So it's not just a theory of functions, it's also a theory of properties and relations, and it might even be a foundational system for all of mathematics. Okay, well, that was a really interesting exploration of the lambda calculus. So let me try to summarize some of the key takeaways for you, the listener. So we started by looking at the basic.